Here's a picture again of the ATLAS experiment. Um, we have here at the top left, we have looking down the beam. We have these things going off sideways. I told you that's what didn't happen in normal events. So we're trying to trigger on this dramatic dramatic energetic particles going off transverse to the beam. And this is, run 190.878 event 272.1965, and this remarkable event happened. It's very, very rare. And here is it shown actually within the apparatus. Here's where the beam comes in here. The other beam comes in there. They collide here, and then they offshoot. And then these things at the side are where most of the measurement is done. You do not measure in detail the particles go very fast in the direction of the protons, because it's very hard to measure there because there's such a lot of beam material there. And also, it's just not interesting. You do not get interesting physics from that. You get the same physics as we studied for many years, and we're not trying to study that in these experiments. Here's a pretty picture of showing the detailed, but you notice these curved particles. These are curved because this all these experiments have giant magnetic magnets in the actual experiment. They're the magnets that keep the protons going round and round the ring, but there's also, when they collide, you have other magnets which measure the momentum of the particles by bending them. So by the curvature of these tracks, the more curved they are, the lower the momentum, and you can then measure the momentum of the particles. And these are the signals you get when the particles enter so-called calorimeters, which respond to the impact of particles. So this is, these things here are the photons, which are remember one of the decay channels of the Higgs was 2 photons. And as I said, the orange tracks are charged, and they're mainly forward and back. You can see that, but again, there are some sideways. Here's an interesting plot, which is, that's the type of, this plot on the left is the type of thing I used to work on when I was a child. You try to calculate what the cross section or the probability of 2 protons producing something. So the basic probability is up here. It's somewhere around 50 millibarns. A barn is 10 to the minus 24 centimeters squared, and that effectively measures the transverse area of a proton, and is related to the linear size of the proton, which is always measured in Fermis, which Fermi is 10 to the minus 13 centimeters. That square is 10 to the minus 26. And actually, the area of the proton is about 50 millibarns, so that's 5 times 10 to the minus 26. So they're all roughly consistent. We're living in this world of 10 to the minus 13 centimeters. And here we have the usual event. And then back down here, how many orders of magnitude? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Down 11 orders of magnitude, or 12, or 13. Here we have Higgs particles. So they're very improbable. That's why you need this incredible trigger to get rid of the normal events. In fact, when you do measurements, the apparatus has memory, because when you measure in these ionized chambers, they actually remember for a certain length of time. When you're taking data so quickly that you remember several previous events, actually here, this says there's 30 typical events in any one real event. Unfortunately, the memory doesn't matter too much because the typical events do nothing interesting, so it's very easy to ignore them. The chance of getting 2 interesting events is negligible. What is true is you'll get 30 of events up here where there's nothing interesting happening together with one of these. And you just have to remove the stuff corresponding to what's up here. And here, of course, is we introduced Feynman diagrams. Here's the proton, and the proton. You have the Higgs produced, and this one is. We actually showed this Feynman diagram. Two weak bosons, the Z's, and the Z's decay into mu plus, mu minus, and mu plus, mu minus, and that's the 4-lepton final state for the Higgs, which was looked at. Notice you have these different ones here. We have the 2-photon decay mode for the Higgs and the 4-lepton decay mode for the Higgs. So phenomenologists, like I used to be, try to tell people which are the great places to look for Higgs. Where's the signature likely to be? And they give approximate predictions for how the particles would look.